All right, so remember we talked about Kc, the equilibrium in terms of concentration, and then the Kp, the equilibrium in terms of partial pressures of the gases. And so for gases, you can use either one of these two values, and we can actually interrelate the two. So we can convert one to the other. So for example, if we have CS2 as a gas, combining with 4 hydrogens, which are gases, to form a methane, CH4, as a gas, and then 2 H2S's as a gas. We can write its Kc, right, in terms of its concentration, CH4 times H2S squared over CS2 times H2 to the fourth. And then we can write a Kp as well, right? So here we're talking about in terms of concentration. Here we're talking about in terms of partial pressure, right? So the partial pressure of CH4 times the partial pressure of H2S squared over the partial pressure of CS2 times the partial pressure of H2 to the fourth. Right. And so maybe, you kind of want to know the Kc of this reaction, or you want to know the Kp of the reaction, and you look up in your book and maybe you find the Kc. You find Kc is equal to 0.28, but you want to talk about in terms of Kp. So then we can ask, what's Kp? And so we can interconvert the two. I'm going to show you how to derive this interconversion. You don't need to know how to derive this. You just need to know the final answer. So if you don't care, you can kind of skip forward a bit till you get to the final answer. But if you care, then take a look. It's not that long. So it won't be asked to derive. You just need to know how to use the final equation. So I'll put this in this kind of little purple blob will be a stuff that you're not going to really be required to know. So we know gases behave for the most part according to the ideal gas law. So we can say PV equals nRT. You remember that from Chem 101. We can then divide both sides by V to have our pressure be N over V times RT. And then if we think about N over V, this is right here as our moles. Right? N is number of moles, V is volume. And in liters, we can kind of think about it in terms of as the solute. And so we can call N over V as molarity. We can call that molarity. And so then we get P equals mRT. And so if we have a reaction where all of these are gases, AA plus BB in equilibrium with CC plus DD, right? Again, we're pretending they're all gases. We can say that the Kp here is equal to the partial pressure of C to the power of C, partial pressure of D to the power of D, over the partial pressure of A to the power of A, times the partial pressure of B to the power of B. And then for each one of these, we can say, for example, the pressure of A is going to be equal to the molarity of A times RT, right? That's what we kind of found earlier here. And molarity is obviously a unit of concentration. So we can take it a step further and say that it's the concentration of A times RT. And so we can plug this part of the equation in for the partial pressure of A, and then repeat that for all the other ones as well. And so then what we end up getting is Kp is equal to the concentration of C times RT to the power of C, concentration of D, RT to the power of D, over the concentration of A, RT to the power of A, and then the concentration of B, RT to the power of B. And then another mathematical property we can use to further simplify our equation eventually is A times X to the M times B times X to the N is equal to AM times B to the N times X to the M plus N. And so we can use that and apply it to our above equation to separate out some of this stuff here. So we can then say the concentration of C to the power of C times the concentration of D to the power of D over the concentration of A to the power of A, B to the concentrate power of B. And then we can add it to this one, right? We can separate out this other half of this reaction. Whoops, this should be a times here. So times RT, we can combine all of our RTs and put them to the C plus D divided by all the RTs to the M plus the N. Oops, my bad. A plus B. A plus B. And then you can see on this side right here, this is all equal to KC. And then on the right side, we can also say that A to the X over A to the N is equal to A to the X minus N. And so we can simplify the right side even further to get Kp is equal to Kc times RT to the power of C plus D minus M plus N. And then further, we can simplify it into this final equation, the only thing you really need to know, and that's Kp is equal to Kc times RT to the delta N. So you need to know this final equation. Where delta N is the difference in coefficients between the products and the reactants. Right, coefficients of products minus reactants. Another thing you want to make sure is you want to ignore solids and liquids, right? So their coefficients don't come here either, right? So this, at the end of the day, this is really what you need to know right here, and you need to be able to use it as well. So for example, if you have a problem that states solid carbon reacts with 2 sulfur gases to form CS2 as a gas, you can write Kp is equal to Kc times RT to the delta N. And then for this delta N, we can say that this is equal to the products coefficients minus the reactant coefficients. And remember, we ignore the solid. So this CS has a 1 in front of it, this has a 2 in front of it, and then we ignore the solid. So it becomes 1 minus 2, which is equal to the -1. So then you can write Kp is equal to Kc times RT to the -1. And then at this point, you would plug and chug. So check out problem 13.4 in your book, the OpenStax book, if you want to see a worked out example of this. But I won't show you because it's all just plugging and chugging.